This video is on section 1.3, the fundamental theorem of calculus, or FTOC. FTOC comes in two statements, one for an antiderivative and the other for evaluation. We're going to go over proofs of FTOC. And to produce the proof of FTOC, we're going to need a theorem called the mean value theorem for integrals. While we're producing the proof of the mean value theorem of integrals, we're going to need to recall results from Calculus 1. Here we go. This is the statement of the mean value theorem for integrals. The hypothesis is that f is a continuous function on a closed interval a to b. The conclusion is that there is a value c somewhere in this interval such that the function at that input c produces this right-hand side. The right-hand side should be a familiar form. We saw it in the last video, that this is the average value of f over the interval a to b. Okay, so we want to produce the proof of this theorem. And as I mentioned, we're going to need some results from Calculus 1. The first result that we're going to use is the extreme value theorem, EVT. The statement of EVT has as hypothesis that f is a continuous function on a closed interval a to b. And for such an f will produce its minimum value, little m, its maximum value, capital M, and therefore will be trapped between its minimum value and maximum value. Good. So the hypothesis of the mean value theorem for integrals has exactly the hypothesis from EVT. F is continuous on a closed interval a to b. Therefore, we can apply EVT and conclude that f attains its minimum, little m, and its maximum, capital M. Let's recall a graph from the previous video. And that graph was used in establishing the comparison theorem, namely that if we have a function which is trapped between a small value little m and a big value capital M, that we can translate that into a statement for integrals, namely that the definite integral of f from a to b is trapped by little m times b minus a, below and above by capital M times b minus a. Good, so we've used EVT from Calculus 1 and the comparison theorem from the previous section. We are currently doing the proof of the mean value theorem for integrals, and we see that the conclusion requires a statement in terms of a definite integral. And currently we have that definite integral trapped between two values. We would also like to find that the definite integral is being multiplied by 1 over the length of the interval. Well, that can be achieved by taking this compound inequality and dividing each term by b minus a. So let's do that. So every term has been divided by b minus a. And we get that this quantity that we're trying to produce a function output for is bounded between the minimum value of f and the maximum value of little f. All right. we're going to need another result from Calculus 1. And that is the intermediate value theorem, or IVT. So here's the statement. The same hypothesis that f is continuous on a closed interval a to b. Then IVT provides that every value between f of a and f of b, we can find an input between a and b such that the output of that c is this value y tilde. Let's look at a little video to try and understand that. So we have two black dots on a parabola. The black dot to the left has a height of f of a, and the black dot to the right has a height of f of b. The two heights differ. And then we have a point, a blue point, at a height of f of c. The f of c is the y tilde that we had earlier. And for any height that you pick between the heights f of a and f of b, you can find an input such that this function will produce that output. Now let's watch what happens as the black dot to the right changes. Okay, the blue dot jumped from the left portion of the parabola to the right portion of the parabola. And that occurred when the height went from being above f of a to the height being below f of a. Okay. So that's the intermediate value theorem. Here's a nice little assignment investigating IVT. So does IVT say anything? Does it give you any conclusion if the outputs f of a and f of b equal? Second, is the converse true? If you know for every value between f of a and f of b, there's an input producing that value, can you conclude that the function is continuous? So that is followed up in part 3 as a particular example to help you with part 2. All right, that should be fun. Back to the proof of the mean value theorem for integrals. We use the extreme value theorem to find that the continuous function over closed interval AB has a minimum value and a maximum value. We then use the comparison theorem from the previous section 1.2 to produce this inequality involving the integral of f. And with this constant 1 over b minus a in front, this is the average value. But this is just some value y tilde that's bigger than the minimum of little f and smaller than the maximum of little f. But since little f is a continuous function on the closed interval, we know that we can find a value c that as input has as output y tilde. And that is exactly what the mean value theorem for integrals is concluding. In other words, we're done. So in the previous section 1.2, you did computations of the average value. And here this theorem is saying that not only can you find the average value, there exists an input which produces that average value. Very good. So that's the mean value theorem for integrals, and we're going to use that result in proving FTOC Part 1. Let's look at the statement of FTOC Part 1 and do the proof. So FTOC stands for the Fundamental Theorem of Calculus. And there are two parts. This is the first statement. What's the hypothesis? Well, the same hypothesis we've been dealing with, that f is continuous on a closed interval a to b. Good. Then let's make a definition of a capital F as a definite interval from the left endpoint, little a, to x. And as integrand, let's use this continuous function f. Very good. Then FTOC Part 1 says that every continuous function has an antiderivative. Remember that an antiderivative of a function is another function such that its derivative is equal to the given function. Very good. So let's get started with the proof. Here's what we need to conclude. We need to conclude that the derivative of this capital F is the integrand little f. We don't really have any tools to work with, so we go back to the definition of the derivative. We're trying to take a derivative of capital F. So write that down, capital F prime. The definition is in terms of a limit of a difference quotient. So the limit as h goes to 0 of the difference of outputs over small change. Let's do simple manipulations. Let's bring the division by h out into the front as multiplication by the reciprocal of h. And then let's look at this numerator, this difference of f's. Capital F of x is given to us in the statement of FTOC Part 1. This definite integral from a to x of f of t. So that's capital F of x has as upper bound x. Therefore, capital F of x plus h will be the same integral, but with upper bound x plus h. Very good. All right. So what next? Well, the right-hand side involves integrals. And we're going to apply a property of integrals. So the property of integrals that we want to apply is that interchanging bounds comes at a cost of a negative sign. We're going to apply it in the reverse direction, that we can absorb a minus sign if we interchange the bounds. So this integral here has a minus in front of it. We'll change that minus to a plus by interchanging the bounds. Very good. Okay. So that's using a property of integrals. There were many properties of integrals. Let's recall one other. Here's another one. That a single integral can be broken up into a sum of integrals if we find a common value for an upper and lower bound. And then in our expression, we have exactly that. A appears both as an upper and lower bound. Thus, we can go from a sum of integrals and express that as a single integral. So this is going to turn into a single integral with bounds x and x plus h. There we go. Fantastic. Then let's think back to the mean value theorem for integrals, since the mean value theorem for integrals says that the average value is produced by the function. So what is the average value? It's a definite integral multiplied by 1 over the length of the integral. Looking at this definite integral, we have x up to x plus h as the bounds of integration. That is a distance of h between the two bounds. All right, so we can apply the mean value theorem for integrals to this expression and swap it out for a function output. Looks pretty good. Keep in mind that this value c is occurring somewhere between x and x plus h. All right, we're nearly done. So here's the expression that we have. Here's what we're trying to conclude. So we need to get rid of this limit. We have to evaluate the limit. But since c sits between x and x plus h, letting h go to 0, remember the squeeze theorem, then that c is going to be forced into becoming x, which completes the proof. Beautiful. So this is FTOC Part 1. The assumption, f is continuous on a closed interval, and that is enough to produce an antiderivative. Write this down. Every continuous function has an antiderivative. So that's part 1. Let's employ FTOC part 1. Do some examples. All right. So capital F is defined as a definite integral. Take a look on the left-hand side. Capital F is a function of what variable? It's a function of x. Take a look at the bounds of the definite integral. The lower bound is a constant a, and the upper bound is a variable x. The integrand is a function. What is it a function of? It's a function of t. This t matches the differential dt. And we know that t takes values between a and x. Okay. Now, let's get to the question. The question is to compute the derivative of this function capital F. So that means taking a derivative of an integral. Well, that's exactly FTOC part 1. Let's recall. FTOC part 1 says that the derivative of such an integral function is just the antiderivative, is just the integrand. So here is the integrand. Let's look at that again. The integrand is f of t, sine of t over t. But what we want to do is express that integrand f as a function of x. So here is the integrand. It's a function of t. We need to write it down as a function of x. And that's all we need to do. So f of t is sine of t over t, but f of x is sine of x over x. Done. Do another example. Okay, so basically the exact same problem. We have a capital F and we want to compute the derivative of capital F. Well, maybe you've noticed that the variable x is not the upper bound, but is here the lower bound. So we need to address that. We need to interchange the bounds of integration. And when we do that, we're going to pick up a minus sign. So rewrite capital F in an equivalent form where the variable appears as the upper bound, and that'll allow us to apply FTOC part 1. So if we put a derivative on the left-hand side, we put a derivative on the right-hand side, it cancels out the integral, and we look at the integrand and replace the variable of integration with the variable x. This minus in front is just a constant, and constants pull through the operation of differentiation. Good? So f prime is negative radical of x cubed plus 5x. Where did the minus sign come from? Well, the definition of capital F has the variable down below. Properties of integrals allows us to interchange at the cost of a minus sign. Fantastic. Here's an assignment for you. Variation on a theme. X is appearing in the bottom, but 5x squared is appearing in the top. All right, so you're going to need to employ various tricks. Here's a hint. Use properties of integrals. So namely, break these things up. And then in particular on the 5x squared, you're going to want to employ the chain rule. Nice. So that was FTOC part 1. Continuous functions have antiderivatives. We'll next do FTOC part 2. Same idea, we'll do the proof and an example. Okay, the statement of FTOC part 2. We make the assumption that f is a continuous function on a closed interval, a to b, and that f, capital F, is an antiderivative for little f. We know that we can do this by FTOC part 1. Every continuous function has an antiderivative. The statement of FTOC part 2 is that the definite integral can be evaluated by taking the difference of the antiderivative, evaluated at the upper bound, and the antiderivative evaluated at the lower bound. Good. We want to do the proof. All right. So, thinking back a couple of videos, we introduced the idea of a partition. Let capital P be any partition of A to B. Then write out this right-hand side, capital F of B minus capital F of A. Okay. So let's see what's going on here. These do not match up. All right, we're going to have to fix that. So capital F of B matches with capital F of B, but minus F of A is not appearing. No problem. I've added in this term, negative F of x sub n minus 1. Remember that on the partition, x sub n is B. So B is the last term in the partition, and x sub n minus 1 is the second to last term in the partition. Now, if we add add in that term as a minus, but then add it in as a positive, then the net effect is 0. Okay, we're still missing the minus f of a, and it looks like we're trying to establish a pattern here that we're going to add in capital F at every single point of the partition, and we're going to subtract it away with a net effect of 0. And then we want to take these pairings of capital F at its adjacent points in the partition. So if we continue that until we get down to x1, then that's accounted for all terms in the partition except for the endpoints, and the endpoints are xn and x0. All right, good. So make sure that you understand how these are equivalent. Nice. And we need to recall the mean value theorem from Calculus 1. So, in the mean value theorem, we have two conditions required on little f: that it's continuous on the closed interval a to b and differentiable on the open interval a to b. If you have such a nice function, then there is a constant c in the open interval such that the derivative at c is equal to this quotient, which is the slope of the secant line. And you'll recall that the left-hand side is giving you the slope of the tangent at c comma f of c. Okay, so we're going to employ the mean value theorem in our proof of FTOC Part 2. And note that this f prime is set equal to, or is found equal to, a delta y over delta x, a change in the output over the change in the input. Good. So back to the proof of FTOC Part 2. So these pairings that we made of the antiderivative at a point of the partition minus the antiderivative at an adjacent point of the partition, this is a difference in the outputs of capital F. And we can apply the mean value theorem to say that this difference in outputs is the same thing as the derivative of the function at some point ci in between these 2 points, multiplied by the change in input. Very good. Now remember, we're doing the proof of FTOC Part 2, and we know that capital F relates to little f, as capital F is the antiderivative of little f. Let's go ahead and use that. So capital F prime is exactly little f, as capital F is an antiderivative. And then the partition that we took is a regular partition, so the difference between any two consecutive points in the partition is delta x. So for capital F prime, we swap it out with little f, and for the difference of the partition points, we swap that out with delta x. Good. So let's go back to that expression of f of b minus f of a, and then we added 0 multiple times and made certain pairings. And then we're going to use this identity of those pairings written out as little f times delta x. So let's do that first here on the bottom. get f at some c1 times delta x. Over here, we'll get f at some cn minus 1 times delta x. And over here, we'll get f at some c times delta x, cn times delta x. So the right-hand side is then a sum of n terms. So let's use sigma notation to write down this sum of n terms set equal to f of b minus f of a. So f of b minus f of a equals to a sum of n terms. Good. Now these n terms correspond with an arbitrary partition that we picked, but that choice of partition that we made does not depend on this equality holding. Therefore, it's going to hold for any partition. And so we can take partitions of greater and greater number, n, and then limit that expression. Doing so, we're then taking the limit of a Riemann sum. And because the limit of a Riemann sum on a continuous function is equal to the definite integral, well, in fact, we are done. Beautiful. So let's bring that all together. So this is FTOC part 2, which we've just done the proof for. And FTOC part 2 provides a way to evaluate a definite integral. Good. Let's do an example. So here we have a definite integral. The integrand is cosine of x. Think about cosine of x. Do you know a function that you differentiate and you get cosine of x? Yes, sine of x. Derivative of sine is cosine. Well, FTOC part 2 then allows us to use sine at the upper bound minus sine at the lower bound. Sine at the upper bound is 1, sine at the lower bound is negative 1. Take the difference of those two values, and that difference is the value of this definite integral. Beautiful. So here are some examples for you to play with. And that brings us to the end of this video. Thank you very much for watching. See you on the next one.